Hello. topics that Gerry cared about. This year's Neugebauer lecturer is Jonas Zmuidzinas, the Merle Kingsley Professor of Physics here at Caltech. I'll introduce Jonas in a moment, but first I want to note that he joins an illustrious list of Neugebauer lecturers. It's a short list now since we're only in the 9th year, so I can enumerate all of them. George Hillou, Eric Becklin, Andrea Ghez, France Cordova, Tom Sofer, David Hogg, Marcia Reike, and Alicia Weinberg. Gerry Neugebauer was a pioneering astronomer. I think it's not much of an exaggeration to say that Gerry's career was the development of infrared astronomy. He was born in Germany in 1932, emigrated to the US 7 years later. He got his undergraduate degree from Cornell and a PhD from Caltech. And after 2 years working at JPL on the Mariner program, Gerry joined the Caltech faculty in 1962. Gerry worked with Bob Leighton on the world's first infrared sky survey, the 2-micron sky survey. He led the science team for IRAS, the first orbiting infrared telescope, which detected more than 500,000 sources, including numerous galaxies as well as debris rings around stars. He played a key role in the development of Keck Observatory and participated in the first science observations on Keck 1 using the original NIRC instrument, the near-infrared camera. Many of you now know about NIRC 2, which has already become an old instrument. Gerry's impact at Caltech was also through leadership, including as division chair here in PMA and director of Palomar Observatory. There were a series of memorials written after Gerry's death in 2014, and I especially like the one from Tom Sofer, who's here in the audience. Tom wrote, Gerry's foundational contributions to infrared astronomy laid the groundwork for the more than $10 billion in investments in this discipline that many countries have made in their infrared space projects, as well as substantial components of ground-based telescopes. None of this would have happened without the excitement of the discoveries made by Gerry and his students and colleagues. So this year's lecturer, as I mentioned, is Jonas Zmuidzinas. Jonas received his undergraduate degree here at Caltech a few years ago. He did his PhD at UC Berkeley with Al Betts and Chris McKee. The title of his thesis was Far Infrared Heterodyne Spectroscopy of Neutral and Ionized Carbon in Interstellar Medium. It's perhaps not surprising that Jonas's grand advisor was Charlie Towns. After a brief postdoctoral position in Illinois, Jonas joined the Caltech faculty here in 1989 as an assistant professor of physics, and this has been his home ever since. Jonas's work is at the interface of astronomy, engineering, and physics. He has made enormous contributions to the development of submillimeter astronomy instrumentation and millimeter astronomy instrumentation. This includes the development of kinetic inductance devices and parametric amplifiers. His innovations have been crucial to facilities like the Caltech Submillimeter Observatory, CSO, which is in the process of moving to Chile, where it will become the Leighton Charge Found for our telescope, as well as the PRIMA mission. And we're going to hear something about these projects during Jonas's talk. So on top of these scientific and research accomplishments, Jonas has also had a leadership presence here on campus. He served as chief scientist of JPL, and is also director of the Caltech Optical Observatories. So Jonas, we're delighted to have you here today to deliver this lecture. So I ask everyone to please join me.
Thank you, Andrew. It's a real honor to be here, and I see so many familiar faces. It's a real pleasure to have this opportunity to speak and to honor Gerry's legacy. So one of the questions I'd like to answer first is, what are these X's about? Some of you know, some of you don't. As Andrew mentioned, I was indeed an undergrad here many years ago. This is my ID card from freshman year, 1977. And back then, if you wanted to use a computer, you had to get an account on the one time-sharing system, a DEC System 10. And your computer account login name were your 3 initials. And if you didn't have a middle initial, you got an X. So I was JXZ and Gerry was GXN. So therefore, the X's. So this was so long ago. It was just slightly after the launch of the Voyagers. So if you think about that, that was really a long time ago. So as you see here, August and September of 1977. And here on campus, there was this group run by Ed Stone and Robbie Vogt called the Space Radiation Lab. You can see there was a lab in the basement of Downs that's pictured there. You can see in the background are a bunch of magnetic tapes, data from the Voyager missions and other missions they were involved with. In the foreground, you can see a model of the cosmic ray instrument that flew on both Voyagers. So while I was an undergraduate, I had the opportunity to work in this group, and my mentor was Neil Gehrels. Thinking back, I can't imagine how lucky one has to be to end up with a mentor like Neil Gehrels. He was extremely helpful in the development of my career as a scientist. He was also extremely disciplined. Every day at around lunchtime, he would stop whatever he was doing and he would sit at his desk and he would open his copy of Jackson's electrodynamics and he would solve the next problem. And if you've ever had the pleasure of solving Jackson's problems, you'll realize that solving from front to back all of the problems in that book is quite an accomplishment. So that was Neil. My task during this working with the SRL group was to work on the calibration of one of the instruments on Voyager, the electron spectrometer. The electron spectrometer was actually developed by another Caltech undergraduate a few years before me by the name of Stan Whitcomb. You might recognize that name. He played an enormous role in LIGO, and in my view is one of the people without whom LIGO would not have succeeded. So anyway, this is a big fat report that I wrote thanks to Neil and Neil teaching me some of the things you need to know to become a scientist. And here's graduation. That was my car. This is on Cordova, not far from campus, Cordova in Michigan. These are a couple of my classmates. That car was given to me by my high school classmate who went on to career in computer programming and was making a lot of money and felt sorry that I wasn't making any money at all as a student. So he gave me the car that he earned working at McDonald's at high school. There was graduation. Richard Feynman actually participated in that ceremony. I'd managed to take a course from him senior year, Physics 236, General Relativity, was a fantastic course. And in the entire, for the entire year, the two people that sat in front of me in Feynman's lecture were Stan Whitcomb and Ron Drever, who Caltech had just hired to start what became LIGO. And so partway through the course, when Feynman started talking about gravitational waves, we realized that we had two kooks in our class that were going to try to measure that, but they did. So after graduation, I bought a motorcycle. I traded actually my car that was gifted to me. I traded it with another classmate for this motorcycle, and I rode it up to Berkeley. I couldn't carry much on my motorcycle, so one of my classmates who was going to Berkeley and we're going to be roommates carried my stuff. I had two boxes, one box of clothes and one box of books, and those were my worldly belongings at that time. Of course, things have changed over the years. And I got to Berkeley and I went on my first observing run shortly afterwards, and we went to Mauna Kea to use the NASA Infrared Telescope Facility, IRTF. And the instrument was basically a radio receiver operating in the infrared at a wavelength of 10 microns. This is the kind of instrument that made Towns's interferometer on Mount Wilson work. But we weren't doing interferometry, we were doing spectroscopy. And so we were taking, as you can see here, I'll use the pointer to explain what's going on. Let's see, that's not the pointer. Where is it? Try the other one. There we go. There's a laser, a carbon dioxide gas laser. Light from the telescope comes in over here. It's combined it's focused onto a detector. It's a very fast detector. And so the output bandwidth expands over 3 gigahertz. The output of that detector is amplified by a transistor amplifier. And this is a cooled transistor amplifier that we have Sandy Weinrep to thank for. Sandy was working at the National Radio Astronomy Observatory at the time and showed that by cooling these amplifiers, you can get very low noise. And in fact, that's what makes most of radio astronomy work today. Sandy has shown recently that you can get very low noise at room temperature. That's what's making ESA 2000 work. Anyway, so the output of this detector represents the beat frequencies between the laser and the telescope. There's a spectrometer out here dividing that spectrum further into 100 channels. At the end of the day, you get a spectrum with a spectral resolving power of about 1 part in 10 to the 6, a very high spectral resolution. And here's what we observed. It was the first detection of the silane molecule outside the Earth. And here's the object, IRC 102116, and that was one of Gerry's discoveries. And so here you see the Becklin 1969 discovery paper. This was a paper from the Becklin and Leighton 2-micron sky survey. And they detected a number of these objects that were stars that were bright in the infrared. And here is IRC 10216 at the top. And you can see some of the words in this paper. They think it's a star surrounded by an opaque dust shell. And then much later, Eric Becklin writes, it was soon established that this emission originates from dust grains flowing out from the dying star. And this mechanism is now recognized as the main source of dust grains that cause interstellar extinction. And so we were studying the formation of molecules in the envelope of this old dying star, in particular silane. And so this is one example of following in Gerry's footsteps. I'll note that Gerry's PhD advisor before he became an infrared astronomer was Bob Walker, who was a professor of physics here for many years. He was a high energy physicist. In fact, the junior year, I took a quantum mechanics course, Physics 125, from Bob Walker, maybe 4 or 5 years before he retired. So what about this mechanism? What about this statement that dust comes from these dying stars? Well, it turns out that that's not so clear. Another mechanism is that they may come from supernovae. In fact, there's this paper from these scientists in all places, Argentina, saying that, well, maybe we could have dust coming from supernovas. So that was 1967. A few years later, here's another paper by Hoyle and Wickramasinghe saying the same thing, not referencing this 1967 paper at all, publishing their paper in Nature, but basically saying the same thing, that maybe you could get dust in supernovae. And even today, you have papers like this that say, well, you could have both mechanisms, and depending on your assumptions, it may be that supernovae dominate, or maybe these evolved stars dominate. Both are potential sources of dust. And you can read over here that this whole field is getting very interesting because as ALMA and James Webb are looking at galaxies at very high redshifts when the universe was very young, they're still seeing dust. And so clearly the formation of dust happens fairly early in the history of the universe. So rewinding to 1970, we have the beginning of far infrared astronomy. And this is Frank Lowe flying in the NASA Learjet observatory, this telescope on an airplane, seeing that a number of objects, galactic and one extragalactic object, having this big peak in their spectrum at a wavelength around 100 microns. And it didn't take long to understand what was going on. This is basically dust being heated by starlight, re-radiating that energy at much longer wavelengths. And here you can see a variety of papers talking about this, but I'll point you to the one at the bottom, Lyman Spitzer in the 1950s, talking about this exact mechanism and saying that for the Milky Way, you might expect about the same amount of energy being radiated by the dust at long wavelengths as compared to the amount of starlight visible in near infrared wavelengths. So there's a long history to this, going back to Lyman Spitzer. And with the launch of IRAS, this is Gerry's, I'd say, the project that perhaps he's most famous for, with IRAS performing an all-sky survey and discovering lots and lots of objects in the sky. You see the galactic plane, but you see a bunch of dots away from the galactic plane. Some of those dots are galaxies that are shining very brightly in the far infrared. And here's a quote from Eric Becklin's 2016 article about Gerry's career. He's talking about these galaxies that IRAS detected, 25,000 or so of them, but some of them are these so-called starburst galaxies. They may be coming from mergers between two galaxies, triggering an episode of very rapid star formation. That star formation occurs deep inside molecular clouds filled with dust. The energy is captured by the dust grains and re-radiated in the far infrared, which is what IRAS was saying. And so here's one example of that process. This is the famous example of the antennae. Two galaxies merging. In the visible, you see this very dark splotch in interstellar dust, but as you go to longer wavelengths, particularly in the submillimeter from the Caltech Submillimeter Observatory, you see that all the action is really over here. That's where the star formation is happening and it's deeply obscured by dust. So around the time that I showed up as a graduate student at Caltech, we had a decadal survey, and it was called the field report. And here are the results that came out, the various recommendations. X-ray facility that became Chandra, the VLBA, the Very Long Baseline Array that NRA ended up building, something called the National New Technology Telescope that never got built, but other telescopes did, like Keck, large telescopes, and then something called the Large Deployable Reflector in Space, LDR. And for small programs, basically the Caltech Submillimeter Observatory was recommended. So that was the state of play when I was starting as a graduate student at Berkeley. Here's LDR, the Large Deployable Reflector. People understood that the space shuttle was coming, and so we had these authors, Powell and Hibbs. Al Hibbs was one of Feynman's very few graduate students. If you've ever read the book Path Integrals in Quantum Mechanics, I believe it's called, it's that Hibbs. It's the same story. Feynman gave the lectures and Hibbs wrote the book. And so they wrote this article about large space antennas, and here you see something that looks suspiciously like one of Bob Leighton's 10-meter telescopes springing out of the cargo bay of the space shuttle, and this is supposed to be a submillimeter far infrared observatory. So that was the idea of LDR. Gerry, meanwhile, was thinking about other ways of doing long wavelength astronomy in space, and he was a little more practical. And so he was talking about using what he was calling the Large Space Telescope, but really this is what became the Hubble. So he's talking about how the Large Space Telescope is related to IRAS in the same way as the 200-inch is related to the 48-inch at Palomar. In other words, one is a survey telescope, that's IRAS, and one is a follow-up, and he was thinking of using the Hubble as a follow-up telescope at long wavelengths in the infrared. And so there's what things look like for the design of Hubble. Here's the instrument that Gerry was envisioning, not small, 2 meters, liquid helium cryostat that would last only for a year, and after that, things were over. And he was calculating what kind of detectors would you use and what the sensitivity would be. Of course, the primary mirror was not going to be cooled. It's going to be around 300 Kelvin. So there's a lot of glow, a lot of thermal emission coming from the telescope, and it's the random arrival of the photons emitted by the telescope that limits the sensitivity. And he was showing that with the detectors that were available at the time, whether you're talking about silicon photoconductors or you're talking about bolometers, this is the detector that Frank Lowe had invented, they would be sensitive enough so that you would be limited mostly by the background radiation from the telescope itself. Of course, if you want to work at these wavelengths, the better thing to do is to cool the telescope and knock this down and move it to longer wavelengths, which is what PRIMA is going to do as you go here. Also around that time, Gerry was doing submillimeter astronomy at Palomar. he had hooked up with Tom Phillips, who at the time was at Bell Labs. And as you can see from this paper, they were detecting for the first time carbon monoxide, the 3-to-2 transition, slightly shorter than 1 millimeter. Here's Tom's receiver at the prime focus of the 200-inch. And so it was Gerry who played a significant role in getting Tom Phillips to come to Caltech. Tom came, I believe, in 1978 or 1979. And by 1986, he was writing proposals with JPL to do something a little more sensible than the large deployable reflector, a smaller space mission called the Submillimeter Explorer. This proposal didn't go, but eventually all that led to Herschel. It led to collaboration between the United States, between NASA and ESA to do the Herschel Space Observatory, a 3.5-meter far infrared space telescope, where the telescope was cooled to about 80 Kelvin. So here's what happened to LDR. By 1989, you see things are growing. It's now become 20 meters instead of 10 meters. Here's an astronaut with a wrench putting the thing together. You can see what happened to this project. It died under its own weight. And meanwhile, as I was getting into this field at Berkeley, I attended this airborne astronomy symposium in 1984. That's me in the front. Here's somebody else, Frank Lowe, the inventor of the germanium bolometer and one of the early pioneers, along with Gerry, of infrared astronomy. In back is my research advisor, Al Betts, who was Charles Towns' former graduate student. Reinhard Genzel was my faculty advisor. Many of you know that name. Here's Charles Towns himself. Mike Werner was there. Mike, that's you. Mike gave a talk. Mike gave, shoot, did I miss it? Here's Mike. Mike gave a talk about SIRTIF, which at the time was decoded as Shuttle Infrared Telescope Facility. Eventually that became Spitzer. Here's another person, Peter Wanier, I'd like to highlight. Peter had been an assistant professor at Caltech, left, went to JPL. Peter's wife, Louise, was an undergraduate, had been an undergraduate at Caltech. She was the daughter of Phil and Ruth Safman. Phil was a professor here. Paul, in aeronautics or applied math? Applied math, okay, thank you. Louise Wanier, Louise Safman Wanier, was the person who showed up before I was admitted to Caltech at my high school to interview me. And as you'll see later on, Peter and I ended up collaborating on some projects. And finally, Harvey Mosley, whose name will show up later in the story. So here I am flying on the Kuiper as a graduate student. We're not doing 10 micron astronomy anymore. We're working at much longer wavelengths. As you can see, 370 microns, looking at neutral atomic carbon, again, using a laser, basically a radio receiver, laser-based radio receiver, same kind of idea as the 10 micron instrument I showed earlier. And life was hard back then. Our instruments weren't very sensitive. We struggled to just measure a spectrum. Here's a quote from Towns a few years later, 1990. He's saying, what remains is perhaps the most difficult spectral region, and the last to be developed, the far infrared and submillimeter, basically saying you're stuck between using techniques that the optical and infrared people do and the techniques that the radio people use, and in between, you don't have much. The technology is really rather poor. But yet, it's interesting. Here's a nice quote from Sandage. So, as I mentioned, Gerry played a significant role in bringing Tom Phillips to Caltech. Tom, just a year or so before coming to Caltech, had invented a new kind of receiver, superconducting receiver at Bell Labs, the superconducting insulator, superconducting or SIS tunnel junction mixer, which is going to have a profound impact on our field. It was going to make our receivers far more sensitive than they had been. In fact, it's that technology that Tom invented that enables ALMA. This is the one key technology. If you want to understand ALMA, It's really SIS receivers that make it work. It's those receivers is why ALMA has the sensitivity that it does. So after finishing graduate school, I understood I needed to get into this SIS business. I moved to Champaign, Illinois, to start learning about this. It's a little different there than California, as you can tell. My advisor there was Fred Lowe. Many of you probably know him. He was the director of the National Radio Astronomy Observatory during the period that ALMA was getting built. I started working on these SIS detectors for submillimeter wavelengths there. Another person who was there at Illinois was another former Caltech undergrad, John Tucker, who had worked out the quantum theory, rather complicated quantum theory of how these SIS devices work. In a nutshell, a photon is absorbed and allows a single electron to tunnel across the junction. So you get 1 electron of current per millimeter or submillimeter wave photon absorbed. It's a quantum device. It's able to reach the quantum limit of sensitivity, limited only by quantum mechanics. And so at some point during my stay as a postdoc at Illinois, this letter arrives in the mail. As you can see, it's signed by Gerry. And the letter says, we're offering you an appointment as an assistant professor. So that changed my life. Another way that Gerry changed my life. And another interesting thing is that if you have any questions, please call me. You know, people weren't using email back then. You had to call on the phone. My memory of this is a little hazy, but I suspect that we actually did have champagne when this letter came. So we had champagne and champagne. Here's moving day, coming back to California, moving into our house in Altadena. And of course, that meant I started to be able to work on the Caltech Submillimeter Observatory in Hawaii. But mostly, I worked on continuing to develop the SIS technology that I had started at Illinois. You can see this was the version about the time that I left Illinois. It got better in the mid-90s as we were flying on the Kuiper. Eventually, it got used on Herschel. Here you can see a picture of one of our chips that we used, the superconducting device. These 2 slots you see here are antennas. This chip sits behind the lens. The lens focuses the light onto this twin slot antenna, and then we have superconducting circuitry to carry the radiation to the 2 tunnel junctions that are located here and here. So we were learning how to design these things. We were learning how to design superconducting circuits that worked at several hundred gigahertz. As a graduate student, I had written a long Fortran code that was a microwave simulator. It basically was an emulator for the commercially available microwave software, the one package that was available back in those days. And we extended that code to be able to put in these superconducting elements. And we developed this, basically the capability for designing superconducting circuits at very high frequencies. My partner in crime on all of this was Rick Leduc at JPL, who's still my collaborator there. And we started flying these on the Kuiper. Here was our team in 1992. Jeff Blake, professor here, John Karlstrom, who like me was just starting out as an assistant professor, ended up moving to Chicago. He's now very famous. Jocelyn Keene, Tom Phillips' wife, Jeff and Jocelyn had been flying on the Kuiper with Tom, doing submillimeter spectroscopy, so they were very familiar with this business. Dave Miller was an engineer in my group, and then later on we added postdocs, Mike Gaitis, George Ugris, and the group started growing. But you see this instrument, we're flying in September of 1992. We did the flights. On the weekend, my brother got married in Berkeley. So I had to get myself from Mountain View, NASA Ames to Berkeley and put on a tux. That's my wife, Ilya. And this is our daughter, Regina, who was not quite a year old at the time of these flights. The letter from NASA telling us that we got funding to build this instrument came after she was born, and we were already flying before she turned 1 year old. She is now married. We have a little grandson that's actually a little older than Regina was in this picture. That's how much time has gone by. It's scary to look at these pictures. Anyway, all of this ended up leading up to our contribution to Herschel, developing the SIS mixers that worked at 1.2 terahertz, the highest frequency for that technology on Herschel. And in 2009, we had a nice symposium right here at Cahill to celebrate the upcoming launch of Herschel a few months later. And here's Tom and also Thijs de Grauw. They were the two co-PIs of the hi-fi instrument on Herschel. A couple of weeks ago, there was a nice workshop in honor of Thijs's contributions, which I unfortunately missed attending, but I was at least able to deliver a lecture there remotely. So these are the two key people that made Herschel Hi-Fi happen. And there's a bunch of other people. If you look closely, you'll find them. Like here's Mike sitting in the front row, Mike Lerner. Okay, now I'm going to turn my focus to the development of kinetic inductance detectors for the last 20 minutes or so. My interest in this started in, a few years after I got to Caltech. There were these interesting papers being published by Andrew Blaine and Malcolm Longyear, where they were looking at the results of IRAS and saying, okay, these galaxies that IRAS discovered that are bright at far infrared wavelengths, they should exist throughout the universe at all redshifts. Can we make predictions about how many of such galaxies you might find as a function of flux on the sky? So this is the number of objects per square degree. This is the flux. As you go to fainter fluxes, there's more and more of them. But the problem is that in order to find these, you need to cover a wide enough field to have a reasonable chance of detecting at least one or a few, which meant that you had to have a camera. You had to have a camera that was able to get a large enough field of view so you could survey a large enough area on the sky. And that meant you needed to have detector arrays. And eventually, the instrument that did this was the SCUBA instrument on our next door neighbor telescope on Mauna Kea next to the CSO, the James Clerk Maxwell telescope. But the way SCUBA was built was all the detectors were built by hand, individually. It had 37 kilometers, and it was a real pain to build. And it seemed clear that this was an area that was ripe for technological innovation. And I got interested in this. Malcolm Longyear he wrote this review article back in 1971. And if you take a look, he's showing essentially light in the universe. There's a microwave background peak over here. On this side, you have the Partridge and Keeble's prediction, basically of visible and infrared starlight. And in between, there's this paper that nobody read, called this Tucker and Lowe paper in 1967, where Frank Lowe, having seen one or two galaxies that were bright in the far infrared, predicted that there should be a background contributed by all these galaxies. Malcolm Longyear was one of the few people that read that paper, and he'd been interested in this topic since then. And so this got me interested in the problem of making detector arrays. Another way I got interested in galaxies was because of Tom Sofer. Tom wrote a proposal to use our instrument on the Kuiper to try to measure redshifted ionized carbon. Now, the Kuiper is a small telescope, 90 centimeters. It's not even a meter. And so why would you do this? Why would you think of using the Kuiper? Well, the answer was that the redshift, as you can see over here, 2.286, put the ionized carbon line at a frequency of 578 gigahertz, which is rather close to the fundamental rotational transition of ortho water at 557 gigahertz. So the only way to see it is to get up above much of the water in the Earth's atmosphere. You can do it from an airplane, but you can't do it from the ground. And so this was really the only choice. And so we did the search. As you can see, we didn't detect very much, but we got an upper limit that was comparable to the predictions that Tom had put into the proposal. So we were close to the target, but we didn't detect the line. This is probably, I think, the only project that I did, astronomical project, that involved Gerry. Gerry was a co-investigator on this project, but it served to get me interested in the problem. So here's a photograph from one of those observing runs. We had to go to Australia. The reason we had to go to Australia is that Peter Wanier had proposed to look at the impact of Shoemaker-Levy on Jupiter using our instrument. He was interested in trying to find water in Jupiter's atmosphere. And so we did that, but then we had to return to the airport. And when we were returning to the airport, we were looking at IRAS 10214 and got a lot of integration time. So here's a photograph from that time. So how do you build detector arrays in the millimeter, submillimeter? People have been thinking about this for a while. Here's a paper from 1984. It involves Ray Weiss of LIGO fame. He was working in microwave background observations in the 1970s. And they were trying to make an array of bolometers. These are simple devices. Light comes in, heats up the absorber, you try to measure the temperature change. You need a small thermal conductance to the heat sink in order for that temperature rise to be appreciably large so that you can measure it. And the way you do that is you make this thermal suspension where the legs of the thermal suspension are very small. You're trying to reduce the thermal conductivity, and using lithography and patterning silicon was the approach that they were using. They were running into problems. Their thermistor, their thermometer, was made by implanting ions into the silicon, and they were having trouble controlling the variability, the uniformity. And that problem wasn't really solved until the mid-90s. That was done by Hardin Mosley at NASA Goddard. So around that time that I was starting to think about detector arrays, Paul Richards, who was actually on my thesis committee at Berkeley, he and his students published this paper about antenna-coupled superconducting bolometers. Well, we were using antenna coupling for our SIS mixers quite a lot, and this was right up our alley. This is the device they were talking about, a planar antenna. We knew about that. Bandpass filter, we knew how to design that. Impedance transformers, we were doing those all day long. The detector here at the end that they were proposing to use was a superconducting bolometer. They had some ideas of how to do that. Later on, there was probably a better idea in this paper. Here's Mike Nahum. He was Paul's student. John Martinez later became the leader of the Google's quantum computing effort. So these are two rather strong experimental scientists. So they suggested a detector that you could use here that would perhaps be a little more practical in Paul's paper. And so I got interested in that. And at the same time, Andrew Lang came and joined the faculty, and Jamie Bach shortly afterwards came as a postdoc. And we were talking about these very different ideas for how to make detector arrays. And we wrote a proposal to NASA. And the proposal had three different possibilities. Germanium bolometers, basically an evolved version of what Frank Lowe had invented, a superconducting version of that, and then a more radical version using antenna coupling and these microbolometers that Martinez and Nahum were talking about. We ended up focusing on the first option. That seemed like the way to make progress more rapidly, more quickly. And that was the basis of a whole slew of instruments involving this one, Bolocam at the Caltech Submillimeter Observatory, which Sunil played essentially led the project. And so you can see here the devices. This is the germanium thermistor on a silicon nitride thermal suspension. You can make arrays of these because you can fabricate these lithographically. This is the technology that ended up being used in the Spire commercial. 2 years later, there was this very interesting white paper that came out, and the lead author was John Mather. I'm sure many of you know that name, project scientist for Webb, but also won the Nobel for work done with COBE, the Cosmic Background Explorer. And they were talking about doing far infrared interferometry in space, now using telescopes cooled to 4 Kelvin. And they're talking about detector arrays of 10 to the 4 elements that are going to be superconducting. So this is a rather ambitious, you could say, vision that they were proposing. The technology to do this really wasn't there at the time, but they were saying we should be striving to do something like this in the future. And so that got us thinking. And I was involved in this proposal with our former student, Rob Scholkopf, who had by that time become an assistant professor at Yale. Here's Harvey Mosley on that proposal and myself. And Rob had come up with an interesting idea for how to make a detector that could be very sensitive in the far infrared. And John Mather wrote this little blurb about it in Nature. What's making it work is Rob Scholkoff's invention, the radio frequency single electron transistor. But to my taste, all of this was a little too complicated. And I felt that we needed something a little simpler. And so that's what led to the invention of the kinetic inductance detector, a desire to find a detector that you could make in arrays that would be simple and more practical. And the idea is shown here. Photon comes in, electrons in the superconductor are paired. These are the Cooper pairs. There's a binding energy. The energy from the photon breaks one or more of these pairs into single electrons. What that does is it changes the inductance of the superconductor. It also changes the resistance. So if you make a resonant circuit, the frequency shifts. If you measure the shift in frequency, you can tell that photon energy has been absorbed. So that's the basic idea. My co-inventor on this is Rick Leduc, again from JPL. We wrote a proposal. We got a little bit of money. Eventually, this led to a proof of concept paper in 2003. And compared to the other technologies that had been suggested, it had a number of advantages. First of all, you could make these detectors not just one at a time, but you can make arrays using lithography. They're very simple. There's no thermal suspension, no tiny legs that you have to worry about. You can make them extremely sensitive by reducing the volume of the superconductor, which is absorbing the photons. It didn't require use of tunnel junctions, which are notoriously difficult to fabricate. And finally, because these are resonators, you could make a whole array of these things and have each resonator set to a different frequency and read out the entire array using frequency multiplexing. So this is really opening the path to large arrays. And I won't go through this slide in detail. I just want to point out that one way to think about these detectors is that you're essentially just performing an exercise in impedance matching. The detector has an impedance which is mostly inductive. There's a small part which is resistive, which is coming from the small number of single electrons, for instance, the pairs that are broken by photons. And what you're trying to do is you're trying to measure this impedance. And the way to do that is to tune out the inductance. And then this capacitance performs the transformation ratio between that resistance and your amplifier resistance. It's a very simple freshman electrical engineering exercise to design these things. Well, around the time that I got interested in the problem of detector arrays, at some point, Gerry checked in with me and asked me, how's it going? Are you making progress on developing these superconducting detector arrays? And I gave him a long story. I said, we need this sub-Kelvin cryogenics, and we need this equipment, and it's expensive, and I have to find ways of, developing the experimental capability. And Gerry looked at me and he said, "Don't let that stop you." And those words rang in my ears for years afterwards. When I heard Gerry saying, "Don't let that stop you," I said, "Okay, enough with excuses. Let's get this done." And so we started to find ways of getting this done. So here's an experimental setup that we put together. This dilution refrigerator was a hand-me-down from the Planck project. Andrew Lang by then and Jamie had gotten involved in Planck, providing detectors for that. And so we were able to get the refrigerator that we needed to do this testing. Tom Tombrello managed to get a few $100,000 donation from Alex Lira, who was a trustee. So we were able to get the electronic gear that we needed to start performing measurements. We used the leftover cryostat from the Kuiper to start building a little demonstration instrument that we could take to the Caltech Submillimeter Observatory to show that these detectors actually could be used for astronomy, not just testing in the lab. And so those words, "Don't let that stop you." If Gerry hadn't said that, I don't know. Maybe I would have been stopped, but Gerry didn't let me stop. And so we managed to find a way forward. This list of team members is completely incomplete. I have a much longer list coming up later. And so we started developing instruments. There was an instrument called Music, which Sunil led, Jason Glenn led. We started exploring ways of making ever larger detector arrays. This was the so-called MACO instrument that we fielded at the Caltech Submillimeter Observatory. We started to learn how to take these devices and really make practical instruments. And today, here's an example of something that's close to the state of the art. Detector arrays being developed for a NASA balloon project called TIM, Terahertz Intensity Mapper. And you can see that these are kilopixel arrays that are being developed, and not just one kilopixel array, but you have multiple such arrays in a mosaic. And the purpose of this payload is to map the ionized carbon line in this range of redshifts using the technique of intensity mapping. I won't say much about that. So today, these detectors are being used widely in a number of different ground-based instruments for cameras, for spectrometers. They're being used on balloons. Our former student, Ben Mazine, is a professor at Santa Barbara. He's developing these detectors for astronomy at visible, near-infrared wavelengths. The fact that you can make a very high-quality resonator using this structure that we were investigating, so-called coplanar waveguide, that was pounced upon by our former student, Rob Scholkopf, professor at Yale. His group published this paper in 2004 called Circuit Quantum Electrodynamics, and basically transformed the field of superconducting quantum computing. So the fact that you can make these very high Q resonators has had a big impact on superconducting quantum computing. We've invented various devices following the kinetic inductance detectors, for instance, parametric amplifiers I won't say too much about, other than that one of our former undergraduate students is now an assistant professor at Princeton using these devices for dark matter searches. There's been a lot of work on the physics of these devices. I don't have a lot of time to go into. One of the things that plagues us is called two-level system noise. It turns out that two-level systems also plague LIGO. And in fact, there's a lot of analogies between our detectors and LIGO. You're basically trying to measure the frequency of a resonance in both cases. And you have two-level system noise that's perturbing you. There's quite a lot of overlap there. But also just the physics of superconductors and what happens when you apply a strong microwave drive. It's something that's not well described in previous papers like the Natus-Bargeen theory, which uses the Bargeen-Kupfer-Schrieffer theory of superconductivity. We're putting superconductors into a rather unusual physical state when we drive these detectors, and there's still a lot that's not understood about that. So I'll finish up talking about PRIMA, this possible upcoming far-infrared space mission. And I'll start the story in early 2000s. We had a decadal survey in 2000 that had mentioned the idea of doing a far-infrared observatory. The idea here was basically, let's make something like the James Webb, which at the time was supposed to be 10 meters, and let's just cool it further. Let's cool it to 4 Kelvin, and let's make it work at longer wavelengths. The committee thought it was a good enough idea to recommend a small amount of technology funding that never came. But nonetheless, it got everybody thinking, and we were a group of people here at Caltech and JPL especially. Here's Matt Bradford involved with myself, but it involved other people, Jamie Bach, Jason Glenn, a bunch of people. We were writing papers about what you could do with a single aperture telescope, not the interferometry that John Mather had proposed, but with a single aperture telescope, what could you do in the far infrared by doing spectroscopy? So here's an example showing that the sensitivity you could reach would be way better than you would get with version by cooling the telescope. We started working on ground-based instruments to do spectroscopy, and part of this was motivated by the fact that Herschel was coming, that Herschel would be detecting galaxies, and it would be nice to be able to do spectroscopy of these galaxies at millimeter wavelengths. And so we developed this instrument that you can see here called Z-Spec. It used the old-fashioned germanium bolometers, and you can see you have this tangle of wiring that results from the fact that you don't have a multiplex readout. Each detector has to be read out individually by its own amplifier, by its own wires, whereas with kinetic inductance detectors, you're able to do multiplex readout. So here's an example I won't talk much about. Here's a paper galaxy is at a redshift of over 6, discovered by Herschel, but with information about its redshift and its spectrum provided by our instrument Z-Spec on the Caltech Lunar Observatory. I participated in this exercise in 2013, which was supposed to be a vision for the next 30 years of astrophysics for NASA. And we managed to include a far infrared mission on the roadmap that this report described. So that was a help. And then in 2016, we started working on a concept for a smaller mission, roughly a $1 billion class. Now this is called a probe class mission at NASA. As you can see the list of characters involved in this study, the Galaxy Evolution Probe study. And the issue here is that the detectors need to be extremely sensitive. If you're doing imaging, you need a sensitivity that's a few times to the minus 19 watts per root hertz. If you're doing spectroscopy, it needs to be substantially better than that, a few times to the minus 20. If you really want to be limited only by the astrophysical backgrounds, and here you can see what those backgrounds are, at shorter wavelengths, the dotted line is showing you zodiacal light emission from dust grains in the solar system. At long wavelengths, it's coming from the galactic dust, emission by dust in the galaxy. Typical temperature for zodiacal light, for the zodiacal dust grains would be of order of 300 Kelvin. For the galactic grains, it's colder, it's maybe tens of Kelvin, and so that dominates at longer wavelengths. And the kinds of detectors I was talking about in the first part of the talk, the so-called SIS tunnel junction receivers, are simply, that's the wrong technology for this job. They're limited by what's called a quantum limit. That corresponds to an occupation number, photons per second per hertz of bandwidth, about unity. Meanwhile, these backgrounds are down around 10 to the minus 7 in terms of occupation number. So you can't use the SIS technology. You have to just directly detect the photons. It's the only way to do it. So I was also involved in a study for a flagship class mission leading up to the 2020 decadal, the so-called Origins Space Telescope. And this was the state of play at the time. This is sensitivity, smaller numbers going upwards. And this is the number of pixels you could put in an array. And what we needed for Origins, we needed a lot of pixels, and they needed to be extremely sensitive. Whereas the state of play at the time was that there were demonstrations of individual pixels that were very sensitive. There were demonstrations of arrays that were fairly large, but you didn't have both. And so how do you get both? How do you get an array, a large array of very sensitive detectors? That was the challenge. And it seemed to us that kinetic inductance detectors would solve the problem. The evolution of bolometers, you can see over here, the legs are getting very, very skinny. These structures are getting hard to make. You have a superconducting thermistor now instead of germanium. This technology was pushed quite hard, not just in the US at JPL, but also in Europe for the SPICA mission, this collaboration between Japan and Europe that unfortunately collapsed. The mission isn't happening, but they put a lot of work into this technology. They made quite a lot of progress. Not enough, but quite a lot. Meanwhile, also in Europe, there was this European Union Framework Program 7 project called Space Kids. They managed to raise several $1 million to push on the development of kinetic inductance detectors for space. And they made a lot of progress. As you can see here, they'd managed to demonstrate that a lot of the requirements that you would need for an array for space are being met. But there were also issues with the approach that they were taking. There was an issue of could you get to the shorter wavelengths that you would need? Could you actually get the sensitivities you would need? And we proposed essentially, instead of using an antenna to couple the radiation, use an absorber that's over here, and to shrink the volume of that absorber enough so that you could achieve the sensitivity requirements that you would need for a space mission. And so that's basically what happened. This is the history of our field as a function of year, sensitivity improving downwards. Here is Frank Lowe's original 1961 invention of the germanium bolometer. If you go down here, you'll see the scuba camera over here. I'm not quite sure I'm seeing them. Somewhere over here are the detectors for the Spire instrument on Herschel. But here's where we need to get for PRIMA. And the green labels over here are kinetic inductance detectors. They're meeting the goals for both imaging and spectroscopy for a mission like PRIMA. In fact, they're getting so sensitive that they're now detecting single far infrared photons. Here you see detection of photons at 25 microns. This is a paper by my longtime collaborator, Peter Day at JPL. This is the mission, 1,000 times or so more sensitive than Herschel. It's a rather big stride. There's a lot of science that PRIMA can do. I won't describe any of it. I'll just show you nice photographs of the various people involved, including the PI, Jason Glenn, and project scientist Matt Bradford at JPL, a number of other people involved in the science. It's a strong team. Here at Caltech, oops, these are graduate students that I supervise. 3 of them are working on the detectors for PRIMA. Chris Albert, Logan Foote, and Elijah Kane. 2 other students, Simon New, is working on the detectors for the terahertz intensity mapping balloon experiment. Ryan Stevenson is working on kinetic inductance for metric amplifiers, another one of our inventions. So I'm about done. I'd like to say, go PRIMA. There's going to be a meeting here at Hamitman in a month or so, May 19th through 21, discussing the science of PRIMA. You can go on this website hosted by ITAC to learn more about it. I can't possibly list all the people over the years that have been involved in developing these instruments and this technology. This is an incomplete list. I'm 100% sure this is incomplete, but this is not the work of one person. This is the work of many, many people, not just here at Caltech and JPL, but around the world. And we're still having fun. So I'll stop here.
Question.
Yes. Mike. Yeah, that was actually on one of these graphs back here. That's up here, the quantum capacitance detector, QCD. This is also a technology developed at JPL. The principal protagonist is Pierre Echternach, a very good low temperature physicist. These devices are, you could say, related and inspired by the work that's going on in quantum computing. They use tunnel junctions. And in many ways, they're similar to kinetic inductance detectors. You absorb light in a superconductor. The light is breaking electron pairs, except the method by which you measure the fact that the electron pairs have been broken is different. It uses a tunnel junction. One of the issues with quantum capacitance detectors, although they achieve rather exquisite sensitivity, is because they use tunnel junctions, making large arrays that have uniform response is a much more significant challenge than for the kinetic inductance detectors. And so that's why on a plot like this, at the snapshot in time, you see that what you'd had is a single pixel demonstration only. Since then, small arrays have been demonstrated, so they're out here, but for space missions, you need to be out here. Yes. Yeah, so this is technology that our former student Ben Mazine at Santa Barbara is pushing hard on. And the basic idea is the same. Photon comes in, breaks pairs, shifts the frequency of the resonance. Except in this case, the photon has sufficient energy to break a large number of superconducting electron pairs. And so by measuring essentially the height of the pulse that comes out of the detector, you can measure the number of Cooper pairs that have been broken. You can measure the energy of the incident photon. And so you have a detector which not only counts individual photons, it resolves the energy of individual photons, and it provides you a rather exquisite measurement of the photon arrival time down to an order of a microsecond or so. And it's capable of being produced in arrays. And so Shree's question is, how large can the array be? And a separate question is, how good can the energy resolution be? You need to make this device competitive in optical astronomy, you need it to do something that you can't do with CCDs. And that some combination of energy resolution and array size is what you need. There's been progress on both fronts, and both array size and energy resolution. I think some ideas are still going to be needed to get to the, let's say, 1 million pixel scale. Right now, the array sizes are few 10,000 pixels, so you need at least another factor of 10, maybe a little more in array size. Not just brute force, but something more elegant. In terms of energy resolution, in the past few years, there's been a significant breakthrough in understanding the physics of what sets the energy resolution. That has to do with the fact that when the photon is absorbed, initially only a single electron receives all of the energy. And so that electron has several electron volts of energy, and it proceeds to share that energy with other electrons. Eventually, you have this cascade. You have a larger number of lower energy excitation, not just electrons, but phonons in the material. If some of that energy escapes the superconductor during this down conversion process, that can lead to degradation of energy resolution, because that the energy escape is going to be random. And if that energy escape occurs higher up in this cascade process, it's going to have a larger impact on the energy resolution. And so what Ben and his colleagues at Santa Barbara, and then separately another team in the Netherlands at Delft, have shown in the past couple of years is that the energy resolution is dictated by the escape of so-called hot phonons, phonons that are fairly energetic, that are being lost fairly early in this cascade process. And there's ways to fix that problem. Ben and his group did it by putting in a layer between the superconductor and the substrate that essentially doesn't transmit those phonons. And they demonstrated a factor of 2 or more increase in energy resolution. So now that the physics is understood, I think with some cleverness, we can expect to see further gains in the energy resolution. So I'm pretty bullish on continued improvements in energy resolution. Array size, I think it'd be nice to have another idea about how to get another factor of 10 or 100. I've worked on this problem. I've thought about it. Yeah, so 1 to 10 terahertz, that's the far infrared. That's 300 microns to 30 microns in wavelength. That's the wavelength range over which PRIMA will operate. And heterodyne detection is of no interest to PRIMA for the reason I mentioned, which is that when you cool the primary mirror to 4 Kelvin, the photon occupation number drops down to 10⁻⁷. Meanwhile, if you're using coherent detection, your sensitivity is equivalent to a photon occupation of number of 1. So you're orders of magnitude off the sensitivity that you can achieve with direct detection. Nonetheless, if you're interested in doing coherent detection, for instance, for interferometry, and you're willing to pay a rather large sensitivity penalty that comes with it, there are options. So Herschel had receivers that went up to, if I remember, at least 2 terahertz. I'm trying to remember the upper frequency limit of Herschel, but around 2 terahertz. That was not the superconducting tunnel junction technology I talked about, but something else called superconducting hot electron bolometers. That technology can be scaled to higher frequencies with a sensitivity that doesn't really change very much with frequency. So you could potentially push that to 10 terahertz. And I think that would be the technology to beat in that frequency range. Below 1 terahertz, these superconducting parametric amplifiers are looking quite interesting. You can achieve extremely large bandwidths potentially and essentially quantum limited noise. Right. So for PRIMA especially, to reach, there's a couple of issues. Designing a kinetic inductance detector is a bit of a challenge. Fundamentally, it's a simple device. There's an inductor and there's a capacitor that form a resonator. The inductor is the part that's sensitive to light, and you need to make the inductor simultaneously absorb the radiation. However, the inductor needs to make a single electrical path at microwave frequencies. It needs to be a meander of some kind. And so here you see the solution for shorter wavelengths that's being investigated for PRIMA. Here's the meander. It goes up and down like this. It just meanders up and down, but then you see these little kinks, and you see this funny little feature here. You see the size scale here, 400 nanometers. So these lines are rather narrow. They're of order 100 nanometers wide. The design of this structure, the goal is to achieve nearly equivalent absorption in both polarizations. So if you just had the meander and you didn't have these horizontal little features sticking out, it would absorb only vertical polarization, but not horizontal. And so adding these little features, you absorb the horizontal polarization. The fact that the lines are so narrow has to do with the fact that these lines in the meander can't be separated much more than about the wavelength you're trying to absorb divided by the index of refraction of the substrate. Otherwise, this thing behaves like a diffraction grating. So the lines need to be close together, and as a result, the lines also need to be narrow. And so this is done using electron beam lithography at JPL to achieve structures with these kinds of dimensions. So for ground-based work, for building the series of cameras I talked about on the CSO and what other groups have done for other telescopes, those detectors can mostly be made using optical lithography, so considerably easier to fabricate. The use of electron beam lithography is a complication in the fabrication, but it's required to get to both the wavelengths that PRIMA is reaching and the sensitivity that PRIMA is reaching. As always in this business, when you're making your own detectors, fabrication is the most important thing. You have to be able to make them. And because kinetic inductance detectors are relatively simple, you can not only make them, you can make arrays.